Hello and welcome. This is an introduction to Experiment 5, Activity 3. So this activity deals with photoelectron spectroscopy. And so here we're going to deal with the molecule methane when it's struck with a high energy photon of light that an electron may be ejected, but with three different thresholds of energy. Photoelectron spectroscopy, what it usually does is it uses a photon energy that's way higher in energy. So imagine we use a tremendous amount of energy and we take the difference of that energy minus this energy required to actually remove the electron. The electron that's ejected would have that much kinetic energy maximally given to it. So you can look at the like maximum kinetic energy of ejected electrons, and then you can actually find for methane that there's three different electrons given off. There's one that's particularly high in energy, and then two that are relatively low in energy. Now, experimentally, what you're going to find is that the explanation here, if you think of methane, you have the inner core s electrons of carbon. They're going to take the most energy to remove. So those electrons take a lot of energy to remove. So the energy of the ejected electrons are going to be relatively low if they had come from that core orbital. Then the other two electrons are going to come from the 2s versus the 2p electrons of carbon. So you can imagine having your four sp3 bonds, but really you don't have four sp3 bonds. You have four bonds total between the H atoms and the carbon atoms, but one of them is made from the 2s overlap of carbon with those 1s orbitals of hydrogen, and then the other orbitals are made with the p orbitals that are all equally degenerate or triply degenerate. So we're going to have electrons that are ejected from the 2s versus the 2p of the carbon atoms, and their overlaps with those H atoms. We're going to explain why we get two other ejected electrons. So experimentally, there are two types of ionization energies that can be measured. We can measure vertical ionization energies, or what's often called adiabatic ionization energies. The difference is the vertical excitation is the energy simply it takes to remove an electron before the molecule can reorient itself and stabilize its energy. So the vertical energy is sort of the energy it takes to remove an electron from the structure of a molecule without allowing it to change its structure. If you allow the excited structure of that cation to then minimize, that the difference between that minimized structure and the original state would be the adiabatic ionization energy. So the adiabatic, or some people call it the adiabatic energy, is the energy it takes to remove an electron where you allow the cation to optimize its energy. And so the way we can use WebMO here, or a Spartan if you're in person on the computer labs, is you can run an equilibrium geometry calculation or an optimization calculation on CH4 with whatever method you want to use. We're going to start with HF 6311 plus G 2dp, and then we're going to determine the bond lengths and angles for the molecule. We're going to ignore the virtual and unfilled orbitals, and then we're going to like sort of construct an MO diagram. And so maybe we'll take a look in a later video at how we're going to get the energies of the molecular orbitals from the calculation. But we're going to compare the energies of those MOs and kind of construct a MO diagram. And then we're going to use the optimized geometry of methane as our starting point. So in WebMO, you always have this option. I'm just going to click on some random job here. You always have this option to begin a job from that particular geometry. So what we're going to want to do is start a job from some completed job. So what we can do in here, once this loads, is like use this new job using this geometry button here. That'll open the molecule in a molecule window, and then you can start a calculation. So then what we're going to do in the next setup menu is we're going to choose just an energy calculation. That's going to allow us to calculate the energy where we remove an electron by changing the charge state to +1, and then since we have one unpaired electron, that makes the substance a doublet. One unpaired electron, that spins a half. Half times 2 is 1, plus 1 is 2. So our multiplicity calculation for singlet versus doublet versus triplet is 2 times the total spin of the molecule plus 1. So this calculation will compute the energy of the cation with the same geometry as neutral methane, and then from there you can go through some of the data analysis. I think we'll discuss some of the analysis in a separate video. And then we'll do a separate calculation where we actually allow the geometry and energy to minimize. So we do an optimization calculation and then repeat the analysis. And then we go back through this using B3LIP and CCSDT, or just CCSD, and compare their results. So before the next lecture, we're just writing a conclusion and making a presentation on activity 2 and 3 for this experiment. And talking about how isodesmic reactions helped us in the determination of reaction enthalpy, and a little bit about the electron spectroscopy and our results from activity 3. So in a separate video, I'll go through getting some of the MO energies from a methane calculation. So that's our brief introduction to activity 3.